I would just like to ask you, just for this introduction, to show your faces on the camera, just so maybe we have a little bit of a hi before we start the session. And yeah, so just to for the presenter to know that there's people on the other side and vice versa. Um, so. Okay. First of all, the second session will be hosted, will be presented by Professor Franci Posavec. Franci is the head of the Department of Machining Technology Management, also the head of the Laboratory for Machining, and he's one of the, let's say, worldwide most well-known experts in particular topics of machining, especially cryogenic machining. He's been a Humboldt scholar. He's had multiple awards for innovation, and within the circles of the faculty, he's well known both for his extremely prolific work with the industry as well as for his research work. So for sure, one of the, let's say, new age of our new younger professors who's really pushing the whole institution forward. With this short introduction, Franci, I think you'll introduce your lab and yourself as well. The floor is yours, so please go ahead.
Do you hear me now?
Yeah, everything okay.
Perfect. Okay. Hello to everybody also from my side. Rok, thank you for a nice introduction. So, I'm coming, like was said, from Laboratory of Machining, Department for Management of Manufacturing Processes. And yeah, we hold a couple of lectures to students. One of those is also advanced machining processes. The other one you have already heard, CAD/CAM and manufacturing systems. Anyway, I will now present the contents or all the details about the advanced machining processes lectures that are held in the first year of master study. The content of the whole course is composed of 30 hours of lectures. Beside the lectures, of course, we put the equal importance to the lab works. So the students have 30 hours of the lab works, and it's expected that 50 hours additionally students work at home. The topics are related to the machining processes from the beginning or the chip formation to live forces and so on. The whole course is focused on the basic 60%, then trends and state-of-the-art review, like approximately 20%, and 20% is dedicated also to the industrial applications, like examples, case studies that we run or based on the collaboration that we have in the industry. The grading system, it's composed on the based on the lab works and the theoretical exam, and lab works are mandatory. 80% attendance has to be assured by the students. Then when this is performed, or when this is exempt as a positive, or they did all the lab works with the reports and so on, they are allowed to go to the exam. We usually organize also the colloquium, so midterm exams. Half of the content is at that time checked from the students. So let's say the half of the semester and then end of the semester, if both of the exams or those colloquiums are positive, it's treated as that the theoretical part is done. If not, then of course the students can go on the normal exam. 2 exams or 2 chances for pass the exam are just after the finish of the semester, so during the exam period. If that's not enough, or if they were not able to either attend or pass the exam, they can have, or they will have one more chance before the next starting of the next year. That's in September. And yeah, the eligibility criteria I talked already. So it is mandatory that the students first finish the lab works or practical work, and then with that one they can go to the exam. Prerequisites for this course are related to the lectures in the first bachelor degree study. So production technologies 1, physics, then materials, machine elements, and tribology. And the objectives of the course is to give the students the in-depth knowledge on the machining processes, from the basics to the advanced and innovative machining processes and technologies, that they get the knowledge on the development of the technologies, the calculations of costs, loads, tool life, optimization, and the production cycles and so on. Also that they have the knowledge about the predictive models that can be used in machining processes, and to get the idea about the influencing on the machining outcomes or focuses and our criteria. Then to get the feeling about the productivity, costs, quality connected to the machining and the final product. The competences that are expected that the student will gain, it's the understanding of the field of machining processes, being able to evaluate, to predict, and optimize the processes, and of course also the mastering, like it says here, mastering of the fundamental, theoretical, and applied knowledge on the machining processes, machining technologies, as well as manufacturing, broader manufacturing technology. Knowledge expected, it's just leading from the expected competences, and the skills, basically the same. As I said before, maybe the added is also that the ability would be also to critically reflect the machining processes strengths, and even think about the innovative R&D in this field. How do we do the lectures or the whole course? Of course, we have lectures in class. Then on the other side, we have the lab works. In between, we also have the practical works, or more practical work on the in the classrooms, where the students are, beside the theory that they get from the lectures, they are introduced also with the practical work that will be then later demonstrated, used, tried, whatever, in the lab work environment in really small groups. As well, all the lectures are recorded, so the students will have the ability to go through these lectures later. If they were not able to attend, they will have the chance to attend it somehow, or repeat this if something is not clear. So that's why we changed, or we upgraded also the lecturing with modern teaching methods. So like I said, all the lectures in this one are recorded. That's related for now on the master degree level, where we have huge possibility to select. The students have the possibility to choose their own lectures, or they can somehow individualize their program. We have 6 study directions. So 2 in energetics, 1 construction, then mechanics, production, mechatronics. And depends, I mean, when the student decide for one of those study direction, they will get 10 lectures, dedicated lectures to these directions of study. However, beside that, they can choose almost the same amount of lectures from different directions. So 8 individual selected course they can get. And that means they have 18 dedicated lectures that they will attend. And as there is the possibility to select individually what they want, that means all the students will have their own programs. And we face the problem how to assure or give the students this possibility to select the lecture and not overlap lectures or even the lab works in some cases. So solution is in recording of the lecture. So if they cannot attend the lecture in person, they can then later check this at home whenever they want, whenever they have time. So they will have accessibility to all these lectures. The other method that we, or digital solution that we introduced, it's just the answer to the problem before. So if we have a huge selectability or personalization of the program, then the question will be, how can we assure the timetable for the students? So each student will have their own timetable. And so in conventional way that have one table, putting everything in doesn't go anymore. So we now have introduced the app that it's providing the students their own timetable, and they have even the possibility to assure or to somehow prepare their own timetable according to the lab works. So there are different, the same lab work, it's has different groups, so repetition of the lab work, and they can choose their own, the best fit, or their own group that fits best for them. Even for lab works, and they will assign to this lab work via smartphone app, and anytime they will have the possibility to see their own timetable, or even then try to arrange the timetable according to their schedule or availability. The third digital app that we introduced is the digital attendance list. It's app that gives the possibility to the students that they attend, that they prove the attendance to different lab works, even the lectures if they want. It's not obligatory now for the lectures, but for the lab works is. They will see which group they are, where they have the lecture, and then when they go to the lecture, they will prove their attendance. And in any time, anyone from our student office, or from the student, or from the lecturer, or from the lab work holder, they will know who was where. If they were, you can check how is then everything is tracked and easier. This information is easier to be obtained. That's the framework in which one we work, and now going to the advanced machining process lecture. So what we want, or what we can say, is that manufacturing or advanced manufacturing can definitely make life better. So the content of the lecture, we have 15 lectures. Each of the lectures is 2 hours long. So 2 hours per week we have, 15 weeks, the whole semester. We start with the basic kinematics of the machine tools and chip formation. So we introduce here the system, machine tool, cutting tool, workpiece, how they interact, what's the kinematics of the machining processes for different processes, of course, and how it's with the tool geometry and terminologies behind. Then we continue with the second lecture dedicated to the defined geometry machining processes, like turning, milling, grinding, and so on. And we define first the cutting geometry, what's there important, how the chip is formed as a consequence of the chip geometry, of the cutting tool geometry, and what are the basic machining parameters and how they interact with the chip formation. Then we go into the chip formation models, mechanics of orthogonal cut, mechanics of oblique cut, so it's from 2D to 3D. Then the application of the cutting models on wheel machining processes. So we show the practical experiments or practical applications of those mechanics of the chip formation. With the fourth lecture, we go to the machining performance, machinability, how different materials behave in machining, what availability they offer to form the chip, how the machining strategy and criteria can be met in effect, and vice versa. And at the end, how we ensure productivity, what is productivity, what is the material removal rate, and that's a step in the direction into the optimization. Of course, the productivity is not just about time, but also the energy consumption that is related to the cutting process. So in the 5th lecture, we move to the cutting forces. Which forces are then machining? How do we measure them? How do we model them? How do we correlate the machining parameters, or how the machining parameters affects the cutting forces and stability of the process? Then we move from the defined cutting edge to the undefined cutting edge geometry. So like grinding, polishing, and so on. And we define the geometry, what's behind, what's the problem with those processes, what are the benefits, kinematics, limitations of the process. Then from this topic, we move ahead with the problem of the undefined cutting chip geometry, cutting edge geometry, where the heat load or the thermal loads are high in those processes. So we, with the next lecture, we move to the heat conditions in machining processes. So temperature fields in the machining zone, how the heat is distributed, how this affects the machining processes, and how this affects the surface integrity as a quality of workpiece material that is machined. We move on the other side. Heat is not problematic just for the machined workpiece or machined surface quality, but also this affects the tool wear. The tool wear leads to the tool life. So we go to the cutting tool wear. What are the mechanisms of the wear or removing the material from the cutting tool? How the tool life can be modeled. We mainly focus here on numerical or empirical models. Then we go to the cutting tools. Which materials, that's the 9th lecture, which material do we use, why, what's the difference between them, how do they interact with different workpiece materials, where are the trends, usage of different materials, pros and cons. We go to one step further. Cutting tools are nowadays all coated. So why the coating is there, what is the coating, what are the functionalities of the coatings, characteristics, how do we put the coating on the cutting tool, PVD, CVD, how the coating affects the machining process as well, how this affects the cutting tool geometry. When we know everything about the tool wear, about the cutting tools, forces, coatings, then we came to the 11th lecture that emphasized the importance of the cooling lubrication scenarios in machining. So we are talking about the cooling lubrication fluids, cooling principles, lubrication principles, and trends in the directions, trends and directions in the research and development on this field, sustainability, clean, safe, and so on. Of course, a question then rises, do we really need them? And then the answer is in productivity and economy to some extent. This is then presented in the lecture 12. where we cover the planning of technological parameters, constraints in defining those parameters, and how those parameters affect not the productivity, but also the economical aspect. They are contradictory. So we have to know what are our goal, what is our fitness function, and then optimize the machining process. And that's the focus in the lecture 13, where we are focused on high productive machining. We distinguish high productivity from high speed machining. The objective of high speed is completely, to some extent, can be same, but it's more related to the chip formation, and the students are sometimes confused. So we dedicated one lecture to distinguish high productivity, high speed, and then how we can optimize the machining parameters according to the goals or measures. Then in 14th lecture, we combine everything and go over the state of the art and trends via special machining processes. We are talking about hybrid machining processes. Nowadays with the Green Deal and so on, the sustainability elements and trends are there really strong. And on the other side, micro machining, completely other world. And at the end, still, all these micro products have their own desires or quality characteristic that has to be met with the machining process. And the kinematics is basically the same, so we have to go down on special focuses here. The 15th lecture is a guest lecture. We invite one expert from the industry. Usually it's an industrial partner that we already collaborate in research, work with. This is, it can go from the automotive industry or an tool making industry, where they have a lot of experiences, and then they can, from the practical aspect, show the students the importance or usage of the knowledge that they get or they got from the first 14 lectures. Beside that, we started, or we usually do the excursions to the industry. That's normally performed in one of the last 3 Fridays in the semester. This year we were in the LTH company. It's aluminum casting company that's beside the casting also do a lot of machining as a final manufacturing operation before getting the final product. Of course, mainly working on the automotive sector. Yeah, the literature, we have some books, mostly in Slovene, from a bit older ones. Then in 2014, a colleague presented the first book on metal cutting theory and application. Then they have also possibility to go a bit higher with the level if they want. So there are 2 books, one hour sustainability in modern metal cutting processes, and from Professor Artin Touch, manufacturing automation, that goes also in dynamics in modern of geometry and so on. And now a new book is also in preparation. So that was quick overview. I plan to go a bit detail in each lecture, what we show there to the students, and maybe we can later even discuss. So I will have 2 to 3 slides for each lecture now, showing how we go or how we present different topics. So the first lecture was basic kinematics, or is basic kinematics of machine tools and chip formation. We go here into the definition of machining process, chip formation, terminology behind, then how the machining processes as well as the manufacturing processes are divided. So single cutting edge, multiple cutting edge, defined geometry, undefined geometry, continuous process, interactive process, and so on. Then we go on the machining parameters, the influences on the machining processes, the cutting tools, geometry, and then the trends of the research in machining processes that they know vary today. So they, as a main terminology, they get familiar with the orthogonal model, the chip, how this one is formed on the rake phase, what is happening on the flank phase, how is with the thickness of the chip on the plant and the actual chip thickness, how is with the rake angle, flank angle, cutting tool angle, and so on. Then that was the first lecture, right? And then with the second lecture, we go on the fine geometry machining processes. So the turning processes, then single edge broaching, milling. With those we touch to the parameters, the tools, the geometries, the productivity, the number of cutting edges, the parameters in sense of cutting speeds, feet rates, approximately where we are to get the feeling rule of the thumb. Then sawmill, broaching, drilling, reaming, and then we summarize at the end. So, for example, in turning, we go through the kinematics, the chip cross section, all the equations behind how the cycle time is calculated, how the productivity, how the cross section and loads or cross section affect the loads, how we manipulate this with the machining processes, the machining parameters. Then how the cutting inserts looks like, how they are mounted in tool holders, how the loads are transformed. Then geometry, for example, of broaching, what kind of final products can we get or are obtained with that kind of process, how this one differentiate from the turning, milling. Then in the third lecture, we go to the chip formation models. Here we first overview the mechanics of orthogonal cutting, then what orthogonal cutting is, how this one, how we describe this process, how we can model it, what is the shear angle, the shear plane, what is happening in the shear zone, what kind of stresses do we have there, and then the speeds or velocity regimes in all three cutting zone. So the zone of chip formation, the zone of sliding of back face or back surface of the generated chip on the rake face, or the third one, the zone where the machined or generated surface wraps the blank face of the cutting tool. Then we talk about the forces, about the energy transformation, machining power behind, so that we can then use this for the energy efficiency and optimization. Then how the chips look like, what are the chips that should be or the size usually, or what are the unfavorable chips. So we talk about the orthogonal process, then which processes in reality are close to the orthogonal model, then all these models of chip formation. Then we end up with the most simple one, merchant one, and then with the merchant we go to the velocity diagrams, and also then we analyze the merchant law. We will see this later. And we go through all the influences of chip formation. Oh, sorry, I forgot to translate this middle one with the chip formation. Then in the fourth lecture, we go on the machining performances, so productivity and material removal rate, concept in machining and manufacturing, the cycle times and so on, and then how do we machine, how do we test the machining performances, and how these machining performances related to the material, to the machining parameters. And then we go through different materials, iron-based materials, then copper alloys, aluminum alloys, high-temperature alloys, like nickel alloys, titanium alloys, and magnesium, for example. We go through those materials, what is the specific for material, how do we start with the machining process and parameters in particular material groups. Then, of course, we correlate here the tool, workpiece, machine tool, then the technology or kinematics or strategy, and how the material characteristics are connected with the toolware and the efficiency. So to get appropriate tool life. We also touch the Taylor equation, where empirically we can define the tool life, and they get a feeling about how the cutting speed is increasing the productivity, but on the other side, this one is negatively affecting the tool wear and the tool life. Then, of course, in the machinability, there are also questions about forces. So we go to Kinsley equation, how the cross section is affecting in combination with material, the cutting forces, or actually all three components, cutting, feed, and radial or tensile force, how this simple Kinsley equation based on the cross-section, chip cross-section can be upgraded with the rake angle, tool wear, coating, or cooling lubrication fluid. Then with this one, we move to the fifth lecture, the cutting forces. We observe, or we talk about the 3D loads on the cutting tool, how the cutting force components affect the process. Then we go in detail back when we measure the forces, how we transform those forces in macro scale or on the machine process when we measure them. How can we, based on those measurements, go into the chip formation and evaluate the shear stresses in the shear zone, or the friction coefficient, normal tangential force on the rake face, then normal tangential force on the plank face. That's all we can get with, of course, some assumptions. Merchant diagram. Then how the forces not just affect the loads, but also the dynamics. They lead to the dynamics of the process, and in the end to the stability of the process via chatting and so on. So these are some slides from the turning. So we go all down from the 3D to 2D perspective, the turning, then milling, how the chip is formed, and of course also the forces, what is the dynamics in forces, the merchant diagram with this possibility to evaluate different region of the cutting zone, and then the stability. At the end, it's so-called chatter appearance. How can we meet this? How can we model this? And really get a stable process, or process where any disturbances in sense of chip size or the forces can be damped or decreased. In sixth lecture, we now move from the defined geometry to non-defined. We talk about abrasive processes, fundamentals of grinding. We start with the grinding because that's the easiest to explain. The chip, the changing of the chip, the cutting edge, changing of the cutting edge, negative geometry, thermal and mechanical loads. Then how there is needed to condition the wheel, so by dressing and shoeing, and then of course also about the productivity. We compare this with the defined cutting edge geometry processes, and then we go to honing, lathing, and polishing. So we show all the processes, we compare them, then we emphasize the importance of the quality of the final products, because all these processes are low productive, but the focus there is in the quality of the final product. That's not just related to the surface roughness, but on the whole surface integrity. Where is the hardness? It's the residual stresses. It's the thermal affected zone. that is normally negatively influencing the fatigue life or the functionalities of the final product. So we see now that thermal loads are really important. That's why in the 7th lecture we go to sources and consequences of the thermal loads and the high temperatures. How do we measure them? If we are able to measure them, then we get the data. We can improve the process in sense to lower those thermal loads to the particular or to the optimum level, not to the level maximum that we can get, because this can be negatively again influencing the process. We all know if we freeze the workpiece, the cutting forces will be much higher, and of course then the loads and the tool wear will be again higher. So there is the optimum temperature, and with the thermal, following the thermal sources and sinks, we can then talk about the optimum temperature regimes. We talk about the residual stresses because of the thermal plastical loads or mechanical loads. We talk about this conventional way of measuring temperatures, also on the novel trends and innovations on this field. And then go to the 8th lecture with the tool wear and tool life. We talk about the different tool wear mechanisms, from fractures, thermal, chemical, to the depth of cut notch wear, rounding of the cutting edges, thermal shocks. Then we give the comparison, or each of those wear mechanisms is then analyzed. So where the adhesion is happening, how do we prevent this, where the diffusion, abrasion, oxidation is happening, and we usually correlate this one with the thermal loads and the cutting speeds, which are in machining relatively connected. So higher cutting speeds are usually reflecting the higher thermal loads. So that's why we can connect this. How do we measure or characterize the tool wear? How do we measure this? And this will be then later used in the lab works. In the 9th lecture, we go to the cutting tool materials. So we present steels, we present different the materials that are used. Then we go through each of those, so through the carbide materials, ceramics, CBN, diamond. We show them the comparison between the toughness, flexibility, or on the other side, the hardness of the tools, of the materials that are used for the tools, and where the ideal cutting material would be, of course. Then we show some completely opposite idea of the chip formation. So why ceramic is used, what's behind there. The idea is completely different, not to decrease the temperature, but rise the temperature. Why is this so? Then, of course, the tools can be even further improved with the coatings. So we go through the needs of the coatings, functionalities of the coatings, how they are made. So CVD, PVD, multi-layer systems, and how do we characterize the coatings or evaluate the coatings. So we show, so we go through these basics, and then what's the comparison between coatings. So reference is titanium nitride. We all know titanium nitride is for machining. It's not really state of the art anymore. And then we see where was the problem with titanium nitride and how these new coatings are distinguishing or improving the performances. In 11th lecture, we go to the cooling lubrication fluids, like we said before. What is the purpose of those, or the usage of those? Then type of the cooling, the types, different types. How do we use them? How do we maintain them? How do we try to meet them with dry machining, minimum quantity lubrication, and what are the alternative cooling lubrication concepts that are today really hot stuff, or really researched in not just in the research area, but also in the industry. So we go through cooling principle or cooling mechanisms or probabilities, then lubrication probabilities, and of course also the chip removal. That's one of the really important functionalities of the cooling lubrication fluids. We present the alternatives, so dry, minimum quantity lubrication. We even go to cryogenic processing. And of course, we show them that 40% or 14% of the total of all the manufacturing costs is related to the cooling of rotational fluids. And then we come not just to the productivity, but also to the economics. And how can we evaluate the productivity? How do we evaluate the economics in felt fracture? How do we define the tool holder index? How do we define the whole technological plan? And just with the technological plan, you can get the evaluation, or you can do the evaluation of costs. That's why the technological plan, it's need for the economical plan. That's in the 12th lecture. We talk about the different costs, fixed costs, variable costs, and the production costs. Of course, it depends on the focus of the optimization. We vary this, we look from the other perspective of this graph or diagram. Then we go to the optimization. We talk about the high performance cutting, on the other side dry and maybe a bit cost effective machine from the other perspective. You see it like that. Then beside HPC, so high performance cutting, we also have the high speed cutting. What are the ideas there? How to distinguish high performance cutting and high speed cutting? Through the graphs of two live surface integrity cutting forces, thermal loads, and then the productivity or the cutting volume. We go a bit through this productivity. How do they know about the range, about the material removal rate? How this one was improved with the different improvements or developments in the cutting tool and the technology. How do we improve, or when will we get to the high performance cutting, different ways of achieving this? And in 14th lecture, then we go to the special machining processes, where behind is the productivity, sustainability, quality, hybrid machining processes, and micro machining. So we compare, for example, conventional oil-based emulsions with today in the industry. We go to the high pressure cooling lubrication systems, and where we get the products, and we somehow analyze the whole life cycle, if I can say that, the machining process, and then how, for example, dry or dry machining can bring benefits to the machining process via lower loads or costs for cleaning, easier recycling. But on the other side, do we improve the machining process or not? It's a question now. And when we get bottom line, the biggest benefits. Hybrid processes, we go through high pressure jet assisted machining, then laser assistance, plasma assistant, ultrasound, magnetic field, and cryogenic assistance. And at the end, micro machining. We have one of those micro machining machines there in the lab, and that they understand how the chip formation is changed, what kind of kinematics is there, accelerations, problems of preparing the CAD/CAM or CAM technologies for that kind of machining operations. It's a bit different world, even with from the tolerance perspective. After the lectures, we have the practical works. These are 6 classroom, if I can say like that, works, where we go through the machining processes, through the machining parameters. They talk about, or they do some exams on, or some calculation about the cross-section, chip cross-section, related to different basic parameters, speed, depth of cut. How do they get data from the technological databases, what they are used. In the second one, we go to the calculation of the cutting forces. So they would calculate, based on the Kinsley model, the forces. And that means they will have some data from the experiments where they will define the Kinsler model, so the specific cutting force and the constants related to the material. Then of course it's a bit, they have to understand what's the, why do we go to the logarithmic scale or logarithmic scale, how do we get from this exponential function, the Miller function and so on. So they calculate that on their own this. Same is with the tool life. So if they get some data from the toolware, then it's a question how to define the tool life. They are here introduced with the Taylor model. They calculate the model based on the measurements that they are provided to them. So again, the exponential function between the cutting speed and the tool life or the wear, they again calculate back the tool life scenario and how the cutting speed is influencing the tool life. Then they would go to the surface roughness or the quality. They will be introduced to different measures of the roughness. How do they theoretically calculate the roughness from the machining parameters? How do we evaluate the chips? How do we optimize them? This chip formation from the machining parameters point of view, as well as the material. Then when they have now all the knowledge, even practical one in the fifth practical work, they would go to the formation of the technological database. So that's important that we develop or we construct this database. Of course, there are handbooks and a lot of information from the providers of the cutting tools, from the web, but it's a so huge database from different or from all the producers that if you don't know how to use those data are useless. So the students are informed about the info standards or the databases behind for the technological parameters, as well as they go and find the data. They learn how to use the data from the handbooks, from the different tools from the cutting tool producers. And then the sixth lab work or class work is related to the geometrical tolerances on the final products. When you know what you have to get from the machining process, of course, it's a question about the machining parameters as well as the machine tool. And each machine tool has to be geometrically characterized. This is done on different principles. It can be with so-called ball bar tests, with the laser evaluation of the precision of the cutting tool. So they are introduced to these methods. All this, of course, it's the base for the lab works then later. These are really in small group, usually 5 to 10 students in the lab behind the machine, and they do different tasks on their own or with the help of the technical staff, assistants or technicians on the machine tool. So they go then in the lab. Usually these lab works are down duration is 1.5 hours to 2 hours. And for now, they are not really allowed to use the equipment. To some of them, yeah, but normally the technician is behind. But then later, for the bachelor thesis, so the final work or master or PhD, they work alone on those machines. And we give them in this lecture or this course 9 lab works. First one is the machining forces. What they get there is they come to the normally lathe or milling center, which one is equipped with the dynamometer and the measuring equipment, all the equipment. Then they measure and analyze the forces. For example, in turning, they try different operations. They sorry, they try or they test different feed rates, different depth of cuts and cutting speed, and see what is the influence on the cutting forces. Then the second lab work will be on machine surface quality. So they will do, again, that's usually on turning process. From the lab work in the classroom, they calculated the theoretical surface roughnesses. Now they use the same parameters and measure the actual surface roughness. We will correlate this one to the theoretical one and to the machining parameters that they inputted to the process or to the machine tool. Then the third one will be related to the chips. Again, they go on the lathe. They vary the feed rate, depth of cut, cutting speed. They collect the chips. They prepare a really nice table. It's written on the floor, a huge one. I think it's like 2 by 2 meters. It's nice to see. And then they place those chips according to the fit and depth of cut, and then they see how the fit and depth of cut and speed affects the chip breakability. Then they go to the tool wear and tool life. They on a bit tougher to machine material. It's a bit thicker, and we increase a bit the speeds to accelerate the tool wear. Then they measure the tool wear from the beginning, from the new tool to the tool life criteria, and see how the speed, for example, then we can vary the speed, can affect the tool life. Then we have the fifth lab work. It's the quick stop device or chip formation analyzers. We have 3 devices so those quick stop devices for 3 processes: drilling, milling, and turning. Usually in turning, it's because it's the most demonstratable, so it's the easiest to see what's the idea there. We do the machining, and then we suddenly stop the process, so they will be able to analyze the chip or to see the chip that is still attached to the workpiece, and see how the chip is formed, connected to the workpiece. And we are now introducing also the thermal camera. This year, the first year, we got this camera and just to show the students what you can get even from the thermal filming of the process. Then on the 6th lab work, we are going on the milling center that has a special option on it, which one follows the loads on all the servo drives. It's a 5-axis machine. That means we have 5 servo motors for each of the axes, 3 linear and 2 rotational ones, and then also the spindle. So we have 7 signals or 7 information from which they can see how the following of the loads on the machine can improve the process. Then we usually do drilling process with a new tool, Warren tool, and see how the machine is capable of sense this and even stop the process if some catastrophic wear occurs. 7th is the geometrical accuracy. That's also an option on the machine tool. We have the coordinates measuring device connected to the machine tool, where it has the feedback to the machine tool to the compensation. So that means you do the one workpiece. If the workpiece some geometrical entities are falling out of the tolerances, this will be sensed in the CMM connected to the tool. It will be a feedback to the machine tool, and the next workpiece will be improved in geometrical way. So the students see how this works. Then the last two are related to the machine tool and the quality of the machine tool, precision of the machine tool. Each machine can have problems with the time sequence of different axes. This can be nicely seen with the ball bar. So they do analyze with the ball bar on the machine. Usually we do this on a simple engraving machine that was done by one of our students previously. It's a simple engraving machine, 3 axes, and this one is not really, usually not really precise and have some problems with the synchronization of the X and Y axis. Then with ball bar, they will see how to identify those problems. And then the last one is it's the usage of laser on the milling center. Why the milling center has to have precision in the tolerance in the positioning, and this one can be measured with the laser. And then if you know what are the errors, you can compensate the controller to neglect or to decrease the error. So they will do we artificially in the controller delete all the compensations, then they will do the laser, and with the measurements they will do the compensation in the controller again. So they know how to improve the accuracy from the software perspective. Let's see. Yeah, this is everything related to this lecture, and of course, if there is any question, comment, we can discuss. I think we can go with the discussion on in the direction what you are curious or where you see challenges, comments, improvements, whatever.
Okay, thank you very much for the presentation, the overview of how we teach these machining processes to our students. So let's see if there are any questions. Feel free to unmute yourselves and just ask the question or post it in chat, whichever way you prefer. So please go ahead. Okay. There seem to be no questions. Maybe I could just ask you one. And I was wondering that the project itself is related to remote work, and we've had a presentation in the morning from you, one of the guys in your lab from Damir, who was talking about certifications as well for CAM systems, and that you can get a particular kind of a paper basically that supports your expertise. Are you maybe familiar with anything similar to just in the area of understanding the processes, or what would you recommend, for example, for students who are studying these topics and want to be employable in companies abroad? What would you say is the best way to go around this?
Yeah, if I start like that, so when we combine the fundamental of the machining processes or correlate with the CAM, of course, fundamentals are necessary for CAM, and usually the industry doesn't really give the certificates or would expect the certificate from the machining processes, but while for the CAM they do. So I think they completely assume that if you have the CAM certificate that you have all the knowledge also from machining processes. Of course, that's not really true. And when we work together with the industry and you see how this everything is treated in the industrial environment, then you see there is a huge lack of the knowledge there. And I think what you proposed, it should be, it's not pity, but it has to be, it will go in this direction. We did already a step in this direction in sense of or in the way of lecturing the industrial partners that are interested in advanced machining processes. So each year in September, we have normally 2 to 3 days workshop that it's condensed in the advanced machining processes. Some of the topics that we talked today more in general are then focused there to industrial partners. And then they, based on the competences they want from the employees, they send them here to our lab to these workshops. I didn't really answer to a question, but the reason is that there is no such a certificate out, but at the end it would be needed. But it's also true that the students that come from this, so from our faculty, from when they get the master degree, they supposed, or the industry supposed, that they know that they have this knowledge. It's also, maybe just to add, I know that there is one question, but anyway, this program was changed or was upgraded last year. So what I showed is it's less than 1 year old, and the program was improved exactly in this direction to get the information from the industry what they need, and now that's the answer to what extent we can, of course.
Okay, so basically modifying the study program to fit the needs of the environment is really important.
Yeah.
Yeah, we have a question in chat, and it's about actually the quality aspect, and we have a lecture in the afternoon on the quality management. But the question here is, do the measurements include the surface roughness only, or do the students also study like roundness and other types of, let's say, geometrical constraints?
Yeah, no, it's not just roughness, because roughness nowadays it's not enough in the industry. Of course, they start with the roughness, but then they have 2 upgrades. One is the whole topography of the surface. So beside ARA, for example, or RZ, they go on the 3D microscope. They characterize the machine surface. We have dedicated equipment, a Licona confocal microscope that gives you the whole topography of the machine surface. So it's much beyond just the surface roughness, and they are faced with that, or they're introduced to that. On the other side, the roundness and so on, it was a question. It's more related to the geometrical tolerances, or quality of the size or the shape of the final product. And even this one, the trend is going, or the direction in the industry is going into the 100% control of the quality. And that's what one of the lab works, it's directly related to that. So when they get the product out of the machine, out of the process, they can measure some of the characteristics, but the process is going on. So if you want to do this 100% control, each workpiece has to be measured, and then based on the measurements, the closed loop has to be performed with the chem or compensation of the tool, so that the next workpiece will be okay. And that's what the students have one lab work related to that. So yeah, they introduced to them.
Okay, thank you. We have another question, basically, which relates to how we structure the courses. So is this course a prerequisite for CNC? But maybe in general, how do we structure all these topics related to machining, CAD, CAM? What's the structure of the courses?
Yeah, the students have during the bachelor and master degree 3 courses. In the first 2 years, depends on the program, they have introduction to the manufacturing processes. But with manufacturing, I mean, they are introduced to the basic machining processes, the basic bending, the basic plastic injection, the basic alternative technologies, the basic additive manufacturing. So that's, they go a bit into the production field. Then in the second level of the studies, so master degree, they would have 2 lectures or 2 courses, one in the first year, the second one in the second year. The first year will be advanced machining processes. So with that, they get all the knowledge about the chip formation, about the terminology, about the machine parameters, and so on. And then in the second year, they have the chem. So yeah, it's a structure. They get familiar with the manufacturing, and they go into the basics of machining. When they know this, and they get familiar with that, they go into the chem, which is the upgrade.
Okay, thank you. Do we have another question from the audience?
Yes, I have a question. First of all, thank you for this valuable lecture. My question is regarding the labs. Now, in performing the experiments, do you use dedicated equipment for each experiment, or you just use the traditional lathe machine, for example, and you perform the experiments using the traditional turning machine or lathe machine?
Okay. Yeah, thank you for the question. I see the question from two perspectives. One is so the dedicated equipment. We in the lab we don't have we don't differentiate the research equipment and the lab equipment. Our idea is to improve the equipment as much as possible to be competitive with the industry. Of course, that's from the research perspective, but on the other side, also the students have the possibility to work on these machines. And usually, whatever lab work is up to date with the industrial needs and level, then we cannot really go on conventional machines. We have to use the up-to-date, really new machines or equipment. So they work on a Licona. That's something that's, I can say, high-tech. Then if you want to show them the closed loop with the measurement system and the controller, we have to go to the milling center that has this option. Of course, it's mainly research focused, but yeah, if we want to show it, we have to go on this machine. If we want to show the, for example, the extreme case, new cryogenic machining technology, we have this on 2 machines, and it's completely research. It's a new R&D, and of course, if we want to show them this, we have to go to exactly this machine that's capable of doing this. That's one answer. The second answer is if we use. I think that the question was also related to the conventional machines and CNC machines. Yeah, some of the lab work also is on conventional machine tools, but because conventional machine tools offer the students in the view inside the machine. The new machines are completely the same from the kinematic point of view. So there they are able to see the kinematics. There's a nice way behind. The kinematics, then quick stop device, for example, because of the principle of doing these experiments, it's performed on the lathe, on the conventional lathe. So yeah, they get into both. And that's also true that we have 2 or 3 dedicated education machines from IMCO, lathe and milling machine. Usually we don't really show the lab works or do the lab works there, but those machines are for the students that they can operate them by them, so without technician support. That's also the case.
Okay, thank you.
Thank you.
Do we maybe have another question? Okay, so it seems we ran out of questions. So thank you very much, Franci, for the presentation. I just want to remind everybody to save the link for answering the forms for the quality report related to the project at the end of the day. So I've just posted that in chat. Other than that, thank you all for attending. And thanks again to the speaker. So thank you, Professor Pušavec, for the lecture. See everybody in the afternoon for the last session of the day. Thank you, Franci, again.
Thank you. Bye. Have a nice day.
Bye.